はい、それでは時間になりましたので、記者説明会を始めさせていただきます。まず登壇者の紹介をさせていただきます。皆様にお配りした次第にはございませんが、向かって右側よりプロジェクトマネージャーの津田、中央にハヤブサ2マスコット担当の岡田、左側にミッションマネージャーの吉川でございます。津田が運動中抜けておりますので、最初の10分間だけの登壇となります。で、まずは津田先生一言お願いいたします。
He'll be here for about 10 minutes. So let's hear from Professor Tsuda first, because he'll be leaving us after 10 minutes. Let me remain seated as I speak. I thank you very much for coming. I'm Hayabusa 2 Project Manager. My name is Tsuda, Professor Tsuda. Today, MASCOT has been separated onto the asteroid. This is the 3rd of October, Japan time 10:57 and 20 seconds. That's when MASCOT was confirmed as being properly separated successfully, and MASCOT descended toward the surface of the asteroid, and from DLR we received information that landing was confirmed. The Explorer, after having separated the lander, ascended to 3 kilometers. This is lower than the usual altitude, but is engaging in communication with the MASCOT, which is on the asteroid, and this will be continued for 24 hours. The MASCOT, the surface operation, has just started, therefore. Internationally, we have been engaging in this landing operation, and is landed successfully, and MASCOT lander operation has successfully started. So let me officially report to you that this is the case. The MASCOT landing operation had an engagement larger than the ordinary headcount. Other than ourselves at JAXA, we had from NASA, the new space station has supported us, so the support level was larger than usual. For Hayabusa 2, in one region there were 2 antennas dedicated, which are in operation. And then there's the MASCOT team in Cologne, in Germany. The operation center is there, and several tens of operators are engaging in the operation. So in that sense, we have an international team, a large team which has led the operation successfully. So we are relieved that this is the case, and that is all from me. Thank you.
So
we'd like to entertain questions to Professor Tsuda first. So if you have a question, please raise your hand.
Are there any questions? Yes, I see a hand over there.
共同通信の末と申します。先ほど冒頭でもおっしゃっておられましたけれども、今日大きなチームでの成功ということで、また
this is a major large-scale team, and you have achieved a success, and the ejection was successful after Minerva 2, so release was successful. So can you talk about your ambitions going forward and your feelings right now? So Minerva, MASCOT, these were 2 difficult operations, but we were able to clear these difficult targets, which was a major give a boost of confidence to the Hayabusa team. In terms of engineering, of course, what we have done in the past, repeating this success does not necessarily is not always guaranteed, but this time around, in 2 consecutive events, we have succeeded. So this gives us confidence that as a track record of or the capability of Hayabusa 2, I think we have been able to build up our skills. Of course, for Hayabusa 2, the immediate target is to complete all the operations of MASCOT 2. This is the major hurdle that we have to overcome immediately. But then after that, towards the landing and the touchdown of Hayabusa itself, we would like to make sure that everything goes well.
Person in the back, please. Yomiuri Shimbun, Tomiyama is my name. I have two questions. As you said at the outset, European devices have been mounted, and it has descended and landed successfully. Minerva is something that JAXA has developed. So this was an international cooperation which was successful. What is the significance of this? Perhaps you felt you carried a heavy responsibility. Could I have your take on this, please? Thank you. Space exploration is such that when you want to do something big, it's something that is too much for one country. We have to take on a lot of challenges for the sake of mankind. The Hayabusa 2 project was one example where we attempted and we achieved this. Germany, France developed the lander, MASCOT, and in doing this as one single project, over 8 years were spent. Between ourselves and between the Hayabusa 2 projects, there was a technical back and forth, and there was a development, testing, and operation on the trajectory or orbit. We have accumulated all of this. Of course, the technical culture differs between countries, but we were able to understand one another. In the end, we were able to unite as one for this single project to lead us to this success. I believe this is a very good precedent that was set. And also, Hayabusa 2, the probe itself and the touchdown of the Explorer, during the rehearsal, you approached it, but this was interrupted. Minerva came closest. And this time, for the separation operation, you approached up to 50 meters, and it was successful. So descent is something that you have perfected the skills of technology. But looking at Minerva 2 images, there's a lot of boulders. This may pose a concern. What are the positive views on this, and what are some of your prospects for the difficulties that might be encountered? First of all, as for the landing technology, in terms of Minerva, it was landed on the northern hemisphere, and we have come to very close. And this time, we have come closest in the southern hemisphere. We've come to the maximum extent that the Explorer can approach. Of course, before that, we're aiming for the equator as well. So in that sense, what we have targeted in terms of the asteroid, we have been able to technically confirm that we're able to access. Now, in the accessible areas, are there completely flat areas? Unfortunately, we know that on this asteroid there isn't. And so toward landing, Ryugu's surf is very rugged, and it's extremely rugged. So how to overcome that? Well, we've just obtained the data today, so we haven't vetted it. But as we operate the MASCOT, low-altitude observation continues. So we'll like to consider this data toward the rehearsal and the next touchdown. And lastly, in the flow of things that you discussed, approaching and landing is totally different. There's a big gap between approaching and landing. Is that correct? Yes, you are correct. Up until now, we've approached, and the approach itself was something that we were not sure about. There was no confirmation. But now we believe we've achieved it. Now, from approach to actually coming into contact with the asteroid, the degree of ruggedness of the asteroid becomes very relevant, and how the Explorer would respond. And it has to land exactly in the correct spot. Otherwise, the Explorer might be in danger. So there's another high bar that we have to vet and reflect in our operations.
Any other questions? Yes, there are 4 hands that I see, so that will be the end of the questions that we take for now for Mr. Tsuda. The person from the back, please. Creative Nexus. My name is Arimoto. So for the future Hayabusa 2 landing, what is the strategy? Let me ask about your strategy. For example, in the rehearsal number 1, you were supposed to drop the target marker, but in the actual real case next month, are you going to drop the target marker so that you can further increase the accuracy of landing? So the landing, we always had planned to land or drop the target marker, so that is correct, but we are not going to do that immediately with the rehearsal. So in the beginning, at the outset, in the next rehearsal that we are planning right now, the surface, just like last time, from the altitude of 20 to 30 meters to the surface, we would like to make sure, we would like to simulate whether the landing device can be guided correctly. And then for the landing, for the actual landing, the target marker will be dropped. So the procedures are correct, you're just right. But did I answer your question? So do you plan to increase the number of target markers so that you can increase the precision? Is that planned? Hayabusa 2 as a technology to land on the crater, it has this technology strategy called pinpoint landing. And for that, we will have to drop the target marker from in the beginning at the outset. But we're not planning to do that immediately at this point of time.
We'd like to move on to the next question, please. Freelance, my name is Otsuka. Toward the touchdown, the guiding accuracy, I believe, will become very important. And what was the MASCOT descent accuracy and the previous Minerva descent? Have you made any changes in view of what happened then? Yes, the guiding accuracy. This is just a flash report, so this needs to be further vetted. But in the case of Minerva, we believe we could do it at around 10 meters. With regard to MASCOT, I believe the accuracy will be about the same range. To the surface of the asteroid, before coming into contact, the accuracy would be about 10 meters in terms of guiding the Explorer. Minerva 1 to MASCOT, were there any improvements made in the intervening time? We have not made any improvements of the sequence has changed, but after obtaining results of Minerva 1, we have not made any changes for the MASCOT. The rehearsal 2 and for the touchdown, you believe you can do it with the present stance and position? Well, I wouldn't go so far as to say that the altitude will become even lower. So in view of the operation of the MASCOT, I would like to do some more thinking. Thank you very much.
Mainichi Shimbun, my name is Nagayama. With the success of the landing this time around, DLR or CNES, have you received any message from these two institutions to you, Mr. Atsuda, or to JAXA overall? I don't think we have received any messages yet, have we? Well, the science team, we have sent a message, and some people, 4 or 5 people, gave us a response of congratulatory messages, but we haven't received anything officially from these two institutions. And on the Twitter, Mr. Tsuda, after the separation, the release was confirmed, I think you sent a message of good luck, MASCOT. What was the situation back then, and what was your feeling to send that information, that message to MASCOT on Twitter? Yes, that was Gate 3 go or no-go decision, the last decision towards Hayabusa 2. From beyond that point, the Hayabusa 2 will switch to a full automation mode, so that is the final command. So beyond that, even no matter what I send as a command, it will not reach unless the MASCOT is released. So that kind of command is sent. So this time around, as part of my confirmation, the MASCOT team go or no go intent was supposed to be received. So from MASCOT team, a go message was sent. So we confirmed that final intent. And then after that, because we have been engaged for such a long time in this international organization with all these international members. So to all these people, I wanted to send a message that thank you for all these efforts so far. And because of this team, we have been able to enjoy this great teamwork. So we have to leave everything from now to MASCOT. So I wanted to share that message. So that's the reason why I sent this message of good luck, according to what I remember so far right now.
The next question, please. I'm a writer. My name is Arafune. This time, it was an international team that engaged in the operation. So in terms of operation, what differentiated from your previous times, or were there any differences in the feeling? Of course, I felt the heavy responsibility, should I say pressure. The group with which we have engaged in development, these are familiar faces, and we know what kind of people they are, and our communication has been very good. And in terms of technology, we had no concerns, and we have come this far. But DLR, CNES, and in Europe, there was a lot of focus on what we're doing. And in Europe, there's an international conference going on, and there are flash reports being sent to this conference. And having been told this, we receive focus in Japan normally, but we were aware that internationally we were under much focus. So that was more of a pressure than normal, and we felt the pressure. But in terms of technology and engineering, there's no difference between what we've done before and now. And from now on, you'll do the touchdown second rehearsal and the actual touchdown. Is the schedule already firm? What we have communicated before, in middle of October and end of October, there has been no change, but the actual dates and the method or procedure will be explained at the next press briefing, I believe. Thank you very much.
All right, thank you very much. Professor Tsuda has to go back to the operation, so he will have to excuse himself at this point. Mr. Tsuda, thank you very much. So let me excuse myself. Thank you very much for your attention. Okay, now moving on to Mr. Okada, who's responsible for MASCOT. Can you share a few words with you? Should I begin the explanation of the materials?
We just showed you the handouts this morning. Professor Okada will explain using the handouts, and after that, we'd like to entertain questions. For those of you that were present this morning, there was a question then, and I gave an erroneous answer, which I'd like to correct at this point. The micro-omega, whether organic matter can be measured, and I said it should be difficult, but I confirmed with Professor Okada, and he said that a micro-omega infrared wavelength has a wavelength that can measure organic matter. So micro-omega can directly measure organic matter. So I'd like to correct that point. So over to Professor Okada.
はい、それではマスコット担当の岡田と申します。
My name is Okada, responsible for MASCOT. So I'd like to use this handout to explain. As for the MASCOT, the name is Mobile Asteroid Surface Scout. It's an acronym, and development was done by Germany and France. The respective space institutions have played a central role in development, but the actual communication equipment was developed in liaison with a Japanese entity. So Japan was involved in the communication aspect. This is one message which I wanted to convey to you. As for observation device, not only these entities, but the respective universities in France and Germany have been involved. The purpose is such that Minerva was mainly engineering-oriented, but this project is for scientific observation. That's the major thrust of this endeavor. So the weight is about 10 kilograms. Compared to Minerva, the mass and weight is heavier because there are observation instruments. The observation instruments comprise four. There's a camera, a mass cam, and then there's micro omega, that's a microscope, and there's Mara, the radiometer, thermal radiometer, and then you have mass mag, which is the magnetometer, and the size is such that it's 30 centimeters times 30 centimeters times 20 centimeters. It's a box shape, and it's a box shape because of manufacturing considerations, and it's embedded in the Explorer, and it has to come out very smoothly. And for smooth coming out of the device, the block shape was very convenient, and that's why it's a block shape. And moving to the next page, and this is a detail of the device. You have the yellow pillars, that's CFRP material, and it's a type of buffer. These screws are used to attach panels, but in the structure there are almost no screws. CFRP is strengthened plastic, and when it reinforced plastic, when it lands, there are no legs for landing. For making the weight light, we have done away with this, and so it bangs onto the surface. Therefore, the frame, the skeleton, is the buffer. And the electronic equipment and observation equipment thereby will not suffer damage because of the buffering effect of the frame. And the distinctive characteristic is such that Minerva had on the surface a lot of solar batteries, but this one does not. And inside there's a battery. And this is a primary battery, and the life of the battery is equivalent to the life of MASCOT itself. And there are electronic devices which are very compact. If you look at the lower right, on the top there's the battery package, and at the bottom, the square part is the e-box, electronic box. All of the devices and electronics for the devices are in here. And then you have CCOM transceivers. These are the communicating devices. This has been provided by Japan. It's the same one that has been used in Minerva. It's commonly used. There are developments which led to this common use. Compared to the size of the Explorer, the mounting space is very limited, and in terms of weight, it's very difficult. So MASCOT is an international endeavor landing device, and Minerva is demonstration of Japan's engineering technology. If we wanted to do both, there was not enough mounting space, so we've decided to share and make for common use. And the communication device has been provided by Japan. And there is a labor in the electronic box, and that's the rotation. And there's a weight there. By rotating the weight, overall there's a torque generated. The reaction of the torque is used to move or to stand the device up. When it lands, when the device lands, it's like a die. You have to. It does not necessarily land in the correct position. So it flaps, and puts itself into the right position, and by so doing, it starts the observation. By rotating the lever in a strongly, there's a strong torque generated, and the device can move about on the surface. That is the mechanism. And on the surface, there's a GNC sensor. There are two kinds of sensors. One is the solar battery, and it's on each surface of the device. When it lands on the surface of the asteroid, which surface is facing upward? If we know that, we know whether the device is correctly positioned. And there's a small laser LED and a detector. This is a package. And when that side comes into contact with the surface, then a reflection light is detected, and we know that it has come into contact. We know which surface has come into contact with the surface of the asteroid through this. So these are the two types of GNC sensors. The next page, please. This is the descent sequence. Home position is 20 kilometers, and it starts its descent from there. And the last 5 kilometers is such that the explorer moves autonomously or conducts the control autonomously. And so under good control, the device heads for the target. At 60 kilometers, the trigger is started, and the first separation sequence is started. And that part has been explained by Professor Tsuda. And it has proceeded as scheduled. The MASCOT starts at 60 kilometers altitude, and the trigger is put into motion. The actual separation comes a little after this, and the separation sequence, after it's ended, it separates. From several 10 kilometers from the surface, the separation starts. And when it hits the surface, it bounces. It's not like a target marker that lands and stays still. It bounces. And with this, it may land sideways. And with the lever device, we position the device in its correct position. The first day, around the daytime of the first day, we will drop it, and before nighttime, we will continue observation. Ideally, until then, if a settlement occurs before that, an observation starts, that would be ideal, so that the minimum data can be transmitted toward the explorer. If we achieve this, this will be perfect. And as for the battery operation, the life is 16 hours. That is the design. And so therefore, the next day, the second day, we believe that the battery will be active, and during the nighttime the battery is also functioning, and the next day during the daytime, hopping, the change of position starts, and it moves to the next observation point. If you observe at the same point, you can only conduct observation from one point. So multiple point observation is what we're trying to do. If we want to make it jump, we can make it jump a considerable distance. But if we wait too long, the very crucial observation will not be possible. So it's up to them to make the final decision. So it's for them to decide. But I don't believe the hopping will be to such a long distance, to a remote distance. And the second day, operation continues, and night comes again, and then daytime comes again. If the battery lasts, we could operate it the next day. If the battery runs down, that will be the end.
The next page. This is the release operation of MASCOT, and this is when we decide the landing sites from the viewpoint of safety. The box areas there is the Hayabusa 2 touchdown candidate locations. So we have selected several locations for Hayabusa 2, L08 and 07, L04, 5 are still remaining as candidate. And as for MASCOT, they themselves have selected the preferable locations, and they have studied these, and that is represented by the blue dots there. So the blue ones are the areas where it is going to be dropped, and because it is going to be bouncing, so the deviations is calculated by simulations. So once it bounces, we would like to make sure that it will not come into the Hayabusa 2 landing site. So we just wanted to confirm that, and the sites were selected based on out of that consideration. So as it turns out, MA9 on the far right side, that is the #1 priority that we are currently looking at. The MASCOT, when bounces are also taken into consideration, and also there are 4 instruments on the MASCOT. So for all these instruments, what is most convenient, the least inconvenient location was calculated. So the location that is most free of trouble has been selected. And as a result, MA9 is currently given the highest priority. So because there were no interference with the touchdown site, so MA9 was therefore selected. The next page. So the MASCOT landing site. This is the picture of the landing site, the vicinity of the landing site. And on the next page, in the simulation, we have overlapped it and plotted the simulation drawing here. So this is the projected landing location. This is the dots of blue distributed in this area. This is probably the site, the actual location of landing. So the south hemisphere of the asteroid. And finally, I would like to talk about the details pertaining to the release sequence. I just briefly talked about this in the previous slide. So from 20 kilometers here, from this home position, the descent will start. And then at 60 meters, the separation release trigger will be issued. And then at the end, the MASCOT will go down by free fall. So it doesn't really have a speed. So that's the reason why we have to spend some time. So only after that, the separation release will begin. So once the release is started, we have to make sure that the MASCOT was actually separated, and if it's coming down towards the asteroid. For that purpose, the ONC double 2, the sideways-looking camera will be used to take the images, and then after that, the downward-looking camera will then take the pictures to make sure that if the MASCOT was really separated, and if it's coming down with the face down, then ONCT, when the Hayabusa is on the rise, and also #1 will also be utilized. So the Explorer will also take pictures when it's ascending. So because after the bounce, when MASCOT bounces, we would like to confirm that. So we would also like to make sure that at the end of the day, where MASCOT has really landed, of course, we're not really sure if that can be visible, but if it's visible, it is clear. The location could be quite clear, and it is very important that we combine that result of the images with the scientific data. So for that purpose, we also take the images by the camera too. And MASCOT will continue to take observations for 16 hours. So in order to ensure communication during that hours, the altitude will be maintained at 3 kilometers. So the Explorer will hover there at the 3-kilometer altitude. And then after that, it will return to the home position. That's all for myself. Thank you very much.
Could we start the Q&A? Yes, then we'd like to start the Q&A. As we did earlier, if you have a question, please raise your hand. Kinuta from NHK. My question is directed to Professor Okada. On this page, which you have on the screen, at the present point in time, you've separated and you've landed MASCOT successfully. Hayabusa 2, the position of Hayabusa 2, it hasn't gone to the hovering position. Is that correct? Yes, at the present point in time, it's in the process of heading toward the hovering position. And the hovering is not easy. It's an altitude of 3 kilometers. If you want to make it stationary at that altitude, you have to thrust it intermittently to keep it at that height. And so the thrust for hovering is now being made at the moment. And if it successfully goes within the altitude of 3 kilometers, well, that's what we intend to do. And the thrust will be made intermittently to maintain the altitude. The altitude of 3 kilometers, toward the altitude of 3 kilometers, everything is progressing smoothly? Yes, nothing has deviated from what we have scheduled. So it is ascending as scheduled. So if it ascends as scheduled, when will it reach the position of 3 kilometers, the hovering position? Well, approximately a half a rotation from now, 3.5 hours or 4 hours, I believe. From which point hovering starts, that's a question. About 3 kilometers, if it reaches approximately 3 kilometers, and to maintain the altitude of 3 kilometers, that is what we're aiming to do in terms of operations. So it's hard to say at what time, but the schedule says 16 hours. It's very soon. So we will maintain the Explorer at the scheduled altitude from that time.
Right, hi, my name is Murasawa. MASCOT is a lander to conduct observation on site in situ. So Hayabusa is going to bring down some samples, but what is the meaning for this MASCOT to conduct observation for the organic matters or other measurements? What is the significance, scientific significance of conducting measurements by MASCOT? Yes, the sample return. The sampling sequence is that we will shoot the projectile and then receive the take-out of the ejectors. So we will have to make the surface collapse. And then after that, the capsule, when it goes into the atmosphere, it will shake a lot, significantly. So that means the original surface condition will not be maintained already by then. So the MASCOT is going to observe the surface of the asteroid because the biggest significance is that they will be able to observe on the surface as is, based on the original conditions. So that is the most important significance. So we're not saying that the materials properties will change significantly, but the conditions under which they have existed will change a lot. So there is a probability of that inducing some changes. So it is very important that we make measurement on the site on an as-is basis. Then Hayabusa 2's sample to be brought back by sample may not be identical to the conditions on the surface. Yes, because it will definitely collapse. Thank you.
Tomiyama from Yomiuri Shimbun. On the spectroscopic microscope, I'd like to ask about details. The mineral composition is to be investigated. The wavelength, the long wavelength near infrared enables you to see whether there's water or not, or whether what it is composed of. For example, you can talk about water, but the status of water is not ice. It's the OH base, which is attached to the rocks. And there's a specific absorption band. And that wavelength, by looking at the absorption features, the OH base, whether there's an OH base or not, can be confirmed. And the wavelength has been known through on-Earth analysis, and so we'll be investigating. I believe it was several months ago. You looked at this asteroid from a remote area, and you said that there may be a little moisture. So this observation is different from the one you've taken before, so the results may differ. Is the range different? What is the difference between remote observation and what you're doing present? The principle doesn't change, but in the case of remote changing, the footprint size is very broad. It's a wide area. In the case of micro omega, this microscope is such that it looks at several meters in terms of area. And because it's a microscope, a lot of pixels, it can be divided into a lot of pixels. And several 10 microns level you can analyze. So on the average, there may be little water. But if you look at individual particles, you may find something. So if you have a high-resolution microscope, I believe it will be very significant. But look at it another way. MASCOT only moves once, so it's a small lander. So even if you are able to observe something, it does not represent the whole. That is correct. Only the places you have observed you can be sure about. And other than hydration, what other mineral characteristics can you investigate? The absorption wavelength, distinctive features will be what we'll be focusing on. So if there's a mineral and there's a clear absorption, we can take a look at that. There's a lot of hydrated minerals, so the absorption characteristics can be used, and you can say this comes close to so-and-so. And as Professor Yoshikawa explained, organic matter, in the case there is organic matter at a wavelength different from water, you can see, you may be able to see some specific absorption. So if you look at the wavelength, you can tell whether there's organic matter or not. Or maybe it might be difficult to specify the types, but you can, to a certain degree, determine whether they're organic matter or whether there's a lot of it or less. Spectroscopy is a major measuring device. Yes, it's mounted in a lot of explorers. So water or organic matter, a specific wavelength, absorption at specific wavelengths, this can be investigated. But in this case, you are exposing it to the surface of the asteroid. So you're looking at what is reflected back and what is not reflected. The sun's reflection, sunlight reflection will be what we're investigating. So there's what you know about sunlight reflection. And so by looking at this, you can see what is being absorbed. Is that right? Yes, that is right.
My name is Kato from Nikkei. Hayabusa 2, the first touchdown, even before that, the organic matters or the water existence, can that be confirmed before the touchdown of Hayabusa? Well, this time around, with this measurement this time around, there is a probability that we may be able to know that, yes. So once the data is retrieved, you'll be able to make that announcement immediately. Well, immediately is not really known, but I think calibration will take time, I think, because it is going to be done remote sensing. So by remote sensing, it doesn't seem to be that there is a significant amount of substance available there, so it's not going to be a significant amount. So calibration will have to be done meticulously, and only after that we're going to make announcements. So when is it going to be likely to make an announcement? Do you have any timeline in your mind? Well, the earliest would be, I would say, let's say the data has to be properly received to the Earth. We'll try to bring it down back to the Earth as quickly as possible, but I think that will likely take 1 week or so. So then only after that, detailed analysis will be performed. So at the earliest, a few weeks' time. Then, by the end of this calendar year, we'll try to perform and complete the analysis. Thank you.
Otsuka Freelance. My question is directed to Professor Okada. Minerva's surface photograph shows that it's pretty rugged on the surface, so it might be difficult to land the device on a flat surface. The micro-omega's microscope is able to observe even if it's removed at 10 centimeters or at very distances of that scale? That's a very good question. The focal distance is such that it has to be very close. So there's a wide gap. The observation will not go smoothly. So how many centimeters? Could you give me the specifics? The mascots, let's see if there's a photograph of mascot. The micro-omega is protruded, and so that portion comes into contact. That's very important. Maybe in this photograph you cannot see. At the bottom there's a protrusion, 2 centimeters to 3 centimeters protrusion. The tip touches the surface, and it is necessary that the tip touches the surface. So it has to attach, come into contact quite correctly, does it not? Yes, it's very rugged, so you may not succeed at the first landing. So it's difficult to say whether it will be successful at the first landing. So there's a procedure called hopping, and it moves a certain distance. And then there's a mode which allows the device to move several centimeters. So if you're unsuccessful the first time, that's not the end of it. It can move just a little bit and take photographs, and then move just a little bit once again to take photographs. So we're hoping that that will make for a successful observation. And after this, because the surface is rugged, if you make the device hop, depending on how it lands the first time, the jumping is toward one axis only. If it stands up, it may be slanted, and then if you move the weight around, if it's just slanted a little bit, you can put it upright in the correct position. Is that what you're hoping for? The lever is one axis, but it can go laterally. It's prejudiced somewhat, so it can roll in different directions, and that's what we're hoping for. And the observation will be through infrared, such as NILS 3. NILS 3 was 3 micrometers wavelength. Micro-omega wavelength is about the same, is that correct? NILS 3 it's longer than NILS 3's wavelength, approximately 1 micron to 3.6 micron. That is what it is able to cover. 0.99 to 3.65 microns. That's the coverage accurately. And this is related to the previous question. Absorption of moisture, water, is about 2.7 microns and above. And the organic matter absorption is the 3.2 to 3.4 microns. And organic matter absorption, in the case of NILS 3, it wasn't covered. Micro-omega does cover. Thank you.
The person in the front row, please. My name is Arafune, a writer. Your role, Mr. Okada, you're responsible for MASCOT, and in what position, in what capacity are you involved in this project? Like you are affiliated with JAXA, and is that your capacity? You are interacting with the MASCOT project? Can you elaborate? My capacity, all right. So I'm responsible for MASCOT, but I'm not really sure what is the appropriate number of personnel responsible for this project. project, but I'm one of the persons in charge, and I'm engaged in many different activities. At the beginning, by equipping the Hayabusa with a MASCOT, what kind of measurement devices should we incorporate? Because I have a scientific background, I do understand, and I was involved, what would be the right observation devices we should equip the Hayabusa with. So that was the beginning, the responsibility that I took at the beginning, but I'm also involved overall. So the technical interface with the Explorer is one thing that I'm engaged in terms of manufacturing, in terms of data communications, and in terms of mechanical environment. So I have to make sure that the interface is aligned, and so that's one of the engineering responsibility that I had to take. And secondly, in terms of operation, based on practical operations, telemetry and command, those things have been designed. So designing these commands and telemetry, and also land experiments, and before launch, and of course after launch, the checkout after launch, and also this time around, this actual practical operation, including all the inputs of commands, and of course confirmation of the status, and all these coordination activities related to these. And of course, when it comes to overseas, I have been involved in the satellite business at ISAS for such a long time, so I have experience in that regard. So there are things that our overseas counterparts cannot fulfill, so I will take that, back that up by sharing my experience. So those are the major roles that I have played in this project. So in reality, using the observation machine, what kind of science do we explore? That was the beginning of the responsibility, but more than that, I think all the other activities are now, including the interface, is now taking a longer time in my overall capacity. When it comes to the magnetometer, I think because this is an asteroid, there's not so much magnetic field. But why do you have you decided to implement this magnetometer? So when it comes to the magnetometer, of course, the opinions are divided. Asteroid, the primordial asteroid, we don't know what it is like, so the basic observation items should be covered overall. So from that perspective, magnetic field is a basic item that we have to observe. So from that perspective, we have decided to implement the magnetometer, and this sensor has a rich record of implementation in various devices, and it can be miniaturized quite easily. And in the solar system, there's always a magnetic field issued and coming out from the sun. And of course, the weak magnetic field can also be measured. That is very important. So even though the MASCOT attitude changes slightly, the solar wind caused magnetic field should also be measured. So that will allow us to measure the movements. So hypothetically, if the asteroid magnetic field itself, of course, that is the essential goal and target of it. But in addition to that, the MASCOT itself movement can also be identified. The behavior can also be identified. And this time around, this is going to be released and bounces on the surface, and then it's going to come to a standstill. So all these movements and operations can be checked and identified by checking on the magnetic field. So that's another important element of this magnetometer. So this is going to be very important for your future projects too. Yes. In terms of technology, this is already an established technology, magnetometer, but there are several teams responsible for this. So if these teams are going to come into play, yes, what you said applies. And MASCOT release after that. After the release, what is your feeling right now, and what kind of observation records are you expecting to come out from this going forward? So, come again, yes. So after the release of MASCOT, so what is your impression right now? What is your feeling right now? And what kind of observation data would you like to see out of MASCOT coming out going forward? Well, yes, the remote sensing. When we saw this in remote sensing, this was an asteroid that went beyond our expectations. So So once it comes down to the surface, now if we can see data that is beyond our expectations, I will be delighted. Because as far as the camera images are concerned, Minerva has already sent us some images, so that was to some extent predictable. But when it comes to the stereoscopic microscope, maybe something out of the blue that we had never expected could become available. And when it comes to the magnetometer, when it comes to certain fields, maybe the remaining magnetic field might be there, residual things may be there that we hadn't expected. If we can find that out, that would be very interesting. Thank you.
The person now wearing the green jacket, please. My name is Akiyama. I'm a writer. Question is directed to Professor Okada. 2 points of confirmation. The micro-omega. Looking at the material you've given us, a three-dimensional image cube, that's what it says. It can observe 3D. Sample size is 3 cube millimeters. So the target, if it has to be under 3 cubic meters, it has to be sand size, or is the target shape? Does it have to be 3 cubic meters? And the thermal inertia measurement is the purpose of the thermal radiometer. What is the scientific goal of this, the thermal inertia? The image cube is perhaps what you're asking about. The image cube is, you have an image of x-axis and y-axis, vertical and horizontal, and then the wavelength direction is added to this. That's three axial, and that's the image cube. And what you often find is that in the case of remote sensing satellites, what you often find is one space is the space, and one axis is wavelength, and it sweeps the surface. And that's the image cube, 3 dimensions, and it's realized in this way. In the case of micro-omega, it's a little different. You have the 2-dimensional, which is the normal microscopic image, and then because this is a microscope, you shed light, and then you take the images. The wavelength which you shed can be shifted. So 320, there's 0.99 to 3.65 microns is changed through 320 steps. So you take picture by picture, and by so doing, you create an image cube. And the size, a 3 millimeter cube. If you look at one microscope image size, that's 3 millimeter squared, and you'll be able to look at something within this frame. And on the thermal radiator, the thermal inertia, as to what this is, it shows the degree of how difficult it is to change the temperature. And what this means is, in the case of normal rocks or gravel or sand, the state of temperature differs. It may be very porous, it may be very dense, and that's the physical status difference. The scientific composition may be the same, but the physical status may differ. So this is one of the means to look at this difference. When the sun shines, during the daytime the sun shines, and at nighttime it doesn't shine. So there's a temperature cycle. In the daytime it warms up, in the nighttime it cools off. The cycle itself, depending on the porous nature of the substance, differs. If it's very porous, heat does not seep in. So when the sun shines, the heat accumulates in the surface, and the temperature goes up very highly. And then at nighttime, the temperature doesn't cool off from inside. So through radiation, if the temperature is released, then the temperature goes down very quickly. So the mode of temperature rise and temperature going down differs. In the case of porous, there's a lot of difference. So if it's very dense, what has accumulated on the surface seeps into the inside. The surface temperature doesn't go up during the daytime much. At nighttime, the temperature that has seeped in comes out. So at nighttime, the temperature doesn't go down as much. So the daily temperature difference or movements are very small. So if you take the measurements, you can see the fluctuation in temperature and the difference in the fluctuation of the temperature depending on the substance. And this is due to the porous or the dense nature of the substance. Heat transmission differs depending on the porous or dense nature. You don't have to break the substance to find this out. So the thermal inertia investigation is looking at the surface physical status of the matter. So the fact that you can investigate that would mean that the Ryugu asteroid, porous nature of asteroid will be elucidated as a result of this? Is that what it is? If you have a rock which is middle porous, it would show that in the past the mother planet of the asteroid was such that there was some function which caused this middle porous nature rock to form. If the rocks are very, very porous, then it means that this function, this metamorphosis did not occur. And so if you look at the surface rocks, you have an idea of the status of the mother planet in the past.
My name is Hayashi, a writer. This is a question to Dr. Okada. In the afternoon briefing, Mr. Yoshikawa mentioned that European Institute has the track record in this lander. So that's the reason why you have allied with the European Institute. So with this MASCOT, in which area have you been able to benefit from the experience of your European peers? Is it because the structure? Is it the observation devices? Right. When it comes to the instrument, observation instruments, if you wanted to prepare this much in Japan, it was never possible because the European counterparts in the past, they have lots of experience of they have done lots of probes that was designed for landing. So when it comes to high performance, light and lightweight and compact in size, they have a huge track record of developing such instruments. So we have reutilized this technology to build MASCOT. So therefore, in a very short time frame, yet we were able to develop this high performance observation machines in this compact size. And secondly, in terms of technology, Rosetta is a mission for the comet, and the lander, Philae is the name of that, the lander, and that has a size of 100 kilograms. And Philae had lots of battery technology, for example. So this time around, the battery that we have utilized for this project and the CPUs, the computer that we have equipped this with MASCOT. To a large extent, we have made it common with Philae, or the upgraded version from Philae is now introduced in MASCOT. So therefore, in terms of technology, and also in terms of the people who are working on this, in all these aspects, I believe we have lots of experience that we can leverage from our European peers. And with this MASCOT project this time around, when we started off, actually, all these people involved in the Philae project came in to help us take off this project. But of course, they got out of the project to some extent because they had to work on Philae. But after the Philae project was completed, they came back. So in terms of development, in terms of operation, they have provided lots of support and shared their experience with us. So one of the experience that we have been able to receive from them was when the MASCOT bounces, actually the simulation for that. Actually, the Philae members participated in MASCOT. Therefore, they had rich sets of experience. So they were also instrumental for us too. Another point is that, having said that, however, the asteroid Ryugu is now the landing target. So you had to develop this in a very short period of time. So there must have been some challenges that you had to overcome. But were there any difficult challenges that you had to overcome? The biggest challenge that we faced this time around was that on the MASCOT side, this 10 kilogram is the size, and within that limitation, we had to realize many things. 10 kilograms is a very limited weight, and all the necessary observation, scientific observation had to be performed, so that was a very big challenge. The main body's weight is about slightly less than 10 kilograms, and the observation instrument takes about more than 3 kilograms, so more than 30%. So as a proportion, that's a significant proportion. And so the lander main body downsizing, we pursued a lot in that regard. We have tried to reduce the weight of the main body of the lander, so that the miniaturization technology as well as the actual design, we suffered a lot. We had a lot to overcome there. And one more question. You talked about remote sensing earlier, and based on remote sensing, asteroid Ryugu was beyond your imagination, you mentioned. I think that's what you said. So in which regard Ryugu went beyond your expectation? Well, I said it was beyond my expectation because this is asteroid. When we look at it and observe it from the Earth, it's just a point. But so we have to make some predictions based on the limited observation data from Earth. So the form factor, I think we have talked about this several on the press briefing some other occasion. But the shape is like a top shape structure, and the self-rotation speed is not so high, so it's not really a top shape, but we thought that it was more round. That was our prediction beforehand, so that was one thing that went beyond our expectation. And the other thing is about the water absorption. We thought we were able to see it more clearly and visibly, but that was not really the case. That's not really so visible, which was beyond and different from our expectations. So in the surface, so once you come down to the surface and when you start the observation with MASCOT, you expect to see something beyond expectation. Can you elaborate what you mean by that? Would you like to see water? Would you like to see some organic matters? Is that what your expectations? Well, if possible, something that I have never seen. Some substance or mineral that I have never seen, or organic matter that I had never experienced in my life, of course. But when we try to think about it, we try to think that this is somewhat closer to some sort of meteorite. But I think because that's the only thing that we can compare with, that's the reason why we try to say something like that. We use that kind of expression. But if it's totally different from those precedents, that would be very interesting.
Nakajima from Nikkei. The communication device, it's made in Japan. Does it mean that JAXA has developed this? As mentioned earlier, it's used commonly with Minerva. So which entity developed the device? Are you talking about the place, the country, or universe? I'm talking about which university, or so forth. With Minerva, it's common with Minerva. So which is the developing entity of the communication device? It's JAXA, yes. Well, it was developed with a lot of difficulty. In the case of Minerva, from the Hayabusa Explorer, the radio wave was very strong, and from the Minerva, there was very weak radio waves sent, which was counter to what you expected. In MASCOT's communication, did you encounter similar problems, or was that problem solved? Was there no problem of this kind in this case of MASCOT? With regard to communication and the content of the data, it's been sent to MASCOT. We haven't looked at the nature of the data in detail, and we've just sent it to MASCOT, so I am not aware of the details. But in terms of the communication lines, we have confirmed that the data has been properly received. Thank you.
Any other questions? Yes, I see a hand over there.
東京飛び物学会の金木と申します。
東京飛び物学会 My name is Kaneki. Regarding the exterior appearance of MASCOT, based on the document that you have handed out today, page 2 in the flight model, I see the exterior appearance of the MASCOT here. The MLI, the insulator, there's a significant portion cut it out here. So was this launched as is, or is this just for the sake of picture taking? This is the actual state, so this is exposed as is. So if that is the case, then all these, maybe there is a potential that something will be coming in. So can that be covered with the design? Have you devised something by the design? Yes, the camera angle was the only opening that we had in the beginning, in the initial design, but from some point onwards, we have to switch to this design. Was that from some reason? The opening here is because, as far as the interior is concerned, there is for the electronics, there's a shield. So we have made sure that there's a shield that will prevent anything coming into the electronics part. But for the observation, there's an opening here. So we just wanted to make sure that the interference can be avoided. So and in terms of avoiding interference, the structure made more sense. So the radio emission and also the camera are incorporated in this part, and also the radiometer as well as the magnetometer are here. The magnetometer is already covered perfectly. The camera and also the radiometer are exposed, really exposed, and they are looking outwards from this opening. And in addition, all the necessary portion is cut out here. So rather than having just a single hole for those necessary parts, we have decided to take off all these walls here because that made more sense. So that was the decision by the European counterparts. So that was the decision by the European side. Okay.
Other questions? Person in the very back row, please. NBS, Kaneko is my name. MASCOT moisture content might be very different, or this separation of MASCOT, is that very different from the release of the case of Minerva? In order to cancel out the horizontal orientation, thrust was applied in the opposite direction, I hear. Could you give us the details with regard to MASCOT? In the case of Minerva, in the case of MASCOT, the separation speed was of 5 centimeters every second, and so it was controlled very well. That was the design. And so the Explorer side did not have to thrust in the opposite direction. It could separate as is. So compared to the separation of Minerva, it was much simpler. Another point. MASCOT's communication device, you said, was common with that of Minerva. So when you are communicating with MASCOT, you cannot communicate with Minerva? Is that how it works? you can design it so that you can communicate. The communication device is such that it can deal with multiple number of targets in its communication. But actually, in the operation of the MASCOT, it's used in a dedicated way, exclusively for MASCOT. And another point with regard to communication, Hayabusa 2, depending on the attitude, there is an attitude which enables communication with Earth and one which does not enable communication with the device. Is in the case of MASCOT, is there an attitude where communication with Earth is not possible? The last sequence, if you look at the last sequence after separation, when Explorer is in ascent, it says ONCT. ONCT has a very small view, so it scans, and the antenna deviates from the orientation toward the Earth. So for about 35 minutes or less than 40 minutes, the link is off. And at all other times, there is always a link between the Explorer and the Earth. Thank you very much.
パソコン資料の通信が切れてしまったようなので。
バッテリーがなくなってしまった。We have run out of the battery for the personal computer. We ran out of the battery first earlier than anybody else. Okay, so we now like to entertain the next question, if there's any.
よろしいですか。
If no more questions.
はい、それではここで質疑応答まで終了とさせていただきます。この後吉川さんと岡田さんは残っていただけますか。はい、個別取材をされたい方は後ほど前の方にお願いをいたします。予定通り17時からは DLR の記者会見の模様こちらで中継をいたします。当日予約が必要な方はヘッドホンを用意しておりますので、受付もしくは広報担当にお声掛けください。ありがとうございました。
Interpretation service, please contact the press staff at the back to receive the simultaneous translation receiver. Thank you.